Hello everyone! You know how sometimes you work on a very interesting project and you work and do some nice progress until one day you decided, you know what, this is good enough. Let's take a day or two break and then return to it. And a year later you have done nothing. So, welcome to the series of Ophir Learns How to Create a Game. So yes, I wanted to create a game, and this is what you see here. And if I'm creating a game, let's do it with something about mathematics. And in particular, I wanted to choose something about the connection between the 3D world and the 2D world. And in this case, I chose the following idea. You start with this cube, and I want to know, can I cut this cube and unfold it and get from this 3D object a nice 2D shape? So in this case, you can do it. And for example, you need to cut this edge, and this one. And then when you unfold it, you unfold it on this black shape. And then again, you can do it something like that. You can cut here and unfold it. And finally, if you cut here and unfold it, you get exactly the shape, the 2D shape, the shadow of the cube. So this was my initial idea, and this is what I wanted to create. And of course, there are several mathematical directions and game-wise directions that you can take it. But before you can actually create the game, you need to actually program what I have here into the game, into the computer. Now, of course, programming a game inside the computer is not an easy task. I mean, even building the room around me was not simple. However, what I like so much about programming, in particular when it is about mathematics, then every once in a while you find out nice mathematics inside the program. And in particular, I want to talk about one such phenomena in this video. And the question is, how do you construct a cube? So let me tell you what I mean. So this is the cube in this game object. I work with a Unity game engine. And when you work with Unity, you have the option to actually add a cube primitive into the game. The problem with this cube primitive, it is just a one block cube. It doesn't know that it has 6 faces. It doesn't know when one face is next to the other face and you can open it up. So you can't really use it in order to do what I did before. So if I really want to do this unfolding action, I need to write down a new cube. And I need to do something like that. So when we think about the cube, we think about a 6 faces die, right? Because it has 1 till 6. And for each 2 faces which are adjacent to one another, we need to know that they are adjacent. We need to know that there is an edge between them. So there are 12 edges, right? There are 4 around the cube and 4 up and 4 down. And for each edge, there are 2 vertices. So all in all, we have 6 faces, we have 12 edges, and we have 8 vertices. Right? So if I really want to write down a cube that you can open up, you need all of these objects. So we have 8 plus 12 plus 6, 26 objects that you need to create. So at this point, I had 2 options. One is just write all these objects down and hard-coded them into my program. This is not too hard, but on the other hand, this is also not absolutely trivial. You can write down the 26 objects, but maybe you had a mistake. Some minus became plus, some 1 became a 2, and your cube became horrible. Right? And I'm talking from experience. And after you made these mistakes, go and find them. Right? This is really difficult. So this was one direction. The other direction is saying, you know what, my life is way too easy, let's complicate it. So the cube is just one type of a die. Let's add some more. For example, we can look at the icosahedron, the 20 faces die, and the dodecahedron, the 12 faces die. So we already see that these are much more complicated, and if you want to just describe the vertices, it is much more complicated. Right? You have all sorts of roots there, and all in all, each one is 20 plus 30 plus 12, so 62 objects that you need to create, and you need to tell me when you have 2 faces, when they are adjacent to one another, and then there is an edge between them. Right? This is way too difficult. So my life is now really, really complicated, and I already have 3 dice, and there are actually 2 more, or in a more mathematical terms, there are 2 more convex regular polyhedron. So the next one is the tetrahedron, the 4 faces die, and the last one is the octahedron, the 8 faces die. So now I have 5 dice to create, and they're all very difficult. And the question is there some nice structure? Is there some nice symmetries that I can exploit in order to create them? And actually there is, like in many objects in mathematics. And to see them, let's look at the cube and the octahedron. And we can see that in a way they are dual to one another. Right? The cube has 6 faces and the octahedron has 6 vertices. The cube has 8 vertices and the octahedron has 8 faces. And both of them have 12 edges. So they are dual in the sense that I start with the cube, I switch between the vertices and the faces, and I get the octahedron. Right? So maybe I can use this duality. We already saw them before also in the icosahedron and the dodecahedron. Right? Again, both of them have 30 edges, and the 20 and the 12 switch between them. Right? You have 20 vertices in the dodecahedron and 20 faces in the icosahedron, and 12 faces on the one and 12 vertices on the other. And also, by the way, the last one, the tetrahedron, is dual to itself. Right? It has the same number of vertices and faces. So there is some nice mathematical structures and some nice symmetries that we can use. So this is what I want to exploit. And to show you how to do it, let's return back to the standard cube. So now I just want to create all the vertices, but I don't want to tell you, these are all the 8 vertices. I want a nice way to construct them. So let's start with a single vertex. And instead of telling you exactly what is this vertex and this vertex, let me just describe the rotation. So if I know one vertex and I know a rotation around the center of this face, then I get a second vertex, a third one, a fourth one, and then I get back to the origin. So just knowing one vertex and one rotation, I managed to find 4 new vertices. Now I also need the vertices below. So let's look at the rotation around the third face. So I get one rotation, second rotation, and now I have 4 new vertices. And 2 more rotations get me back to the origin. So again, knowing just one vertex and 2 rotations, I get 8 new vertices. So this is really the idea. We have some nice symmetry for the cube, and we use these symmetries in order to find all the vertices. And of course, we can do the same for the edges and do the faces. However, the cube is one of the most simplest of dice, so let's look on another example, a much more complicated example. Let's look on the dodecahedron. So again, I start with a single vertex, and I start with rotation. So I have 1, 2, 3, 4, and 5, and I get back to the origin. Now this means that I found already 5 vertices, and again, I can take the rotation around the second vertex, the second phase, and you can check that you actually don't get all the vertices. I mean, it's not as simple with the cube. So at this point you can say, you know what, maybe I can do also rotations around the first phase and maybe the third phase and maybe the fifth phase. But at this point it becomes much more complicated to describe. And I want a very, very easy way to do it. So let me tell you about this easy way. Again, you start with a single vertex and you start with a single rotation. But instead of continuing this rotation, let's look at the rotation around the origin vertex. So I have 1, 2, and 3. So all in all, just doing 1 rotation here and 3 rotations here, I get these 4 vertices. And there is something nice about these 4 vertices. Right? I started with the red vertex, and I managed to find all of its neighboring vertices. Okay, so there is this very nice property coming from the symmetry of this dodecahedron. And here comes mathematics with all of its beauty and saying the next thing. If you look at all the rotations with this face and with this vertex, so maybe 1 rotation here and 1 rotation here and maybe 2 rotations here and another 5 rotations here, and you take all the compositions of these rotations, then you get a nice structure called a group. Right? A group, this is one of the nice structures in mathematics which actually used to study symmetries of an object, for example, symmetries of dice. And it appears almost everywhere. Now these groups have very, very nice properties, and in particular one of these properties in our case says the following. If you started with a single vertex and managed to find all of its neighbors, then this is true for every vertex. So for example, we know about this blue vertex, and its 3 neighbors is the red one, which we already know, and there are actually 2 more here. So the same is true for this vertex. There are 2 more neighbors here and 2 more neighbors here. So all in all, we started with the red, found all these blue neighbors, and from the blue we can find all the green neighbors. So we have 1 and then 3 and then 6. And now you can continue. If you know about all these 6 green neighbors, you can find all the pink neighbors, and then you can find all the teal neighbors, and finally you have 1 more black neighbor here. So again, we started with just 1 vertex, the rotation around this vertex, and rotation around this face, so 2 rotations and the position of one vertex, and we managed to find all the vertices of this dodecahedron. So this is really the strong thing about mathematics, and in particular the group theory, that you can use the symmetry of an object to find a lot of information about it. Okay, so we already saw how to use this information to create the dice. Let me tell you one last thing. And again, let's return to the original cube. And remember, you start with a single position of a vertex, and then you do also sort of rotation. So you can do rotation around the face and rotation around the vertex, and you get all the vertices and all the faces and all the edges of the cube. And now I have a nice new question. Let's suppose that instead of starting with this vertex, I start with a vertex in another position. For example, I start with a vertex at the center of a face. And remember, this was the duality. I wanted to move from faces to vertices and from vertices to faces. So if I have an extra vertex in the middle of this face, then I should have an extra vertex in the middle of all the faces if I want it to be closed under these rotations of the cube. And then suddenly I get something like that. Right? So I started with this vertex and do all of the rotations around the vertex and around the cube and around the faces. And suddenly I get a new die. Right? And if I inflate it some more, I get exactly the octahedron. So again, we started with the cube, we looked at the symmetries, at the group of symmetries of the cube, and then said, if we started with a different vertex in the middle of the face of a cube, we get another general cube, right? We get the octahedron. And again, here we have rotations around the faces and rotations around the vertices, and we get exactly the same group of symmetries. Okay, I think that this is all. And again, the idea is that we have very, very nice groups of symmetries. This is what I use in order to create this polyhedron, these dice, and this is what I use to move from one to the other. And that's all. So if you excuse me, I need to go refactor the code, so the next time that I work on it won't be a year from now. And let me give you 10 points bonus for anyone who can identify all the mathematicians in this video. Okay, I'll see you next time.